Here is a vector arrow floating in three-dimensional space right from the very first second. A vector has direction and length, and in 3 dimensions that single idea is about to unlock lines and planes. Let's write a vector in component form. Here is vector v with components 2, 3, and 6. Before we calculate anything, take a guess. What do you think the length of this vector might be? To find its length, we use a 3-dimensional version of the distance formula. Magnitude of v equals the square root of 2 squared plus 3 squared plus 6 squared. That's the square root of 4 plus 9 plus 36, which is the square root of 49, so the magnitude of v equals 7. Now let's describe a line in 3 dimensions. We only need 2 things, a point sitting on the line and a direction vector to travel along. Take the point 1, 0, 5, call it A, and the direction vector 1, 2, minus 1, call it D. The line is written as r equals a plus t times d, where t is a parameter that can take any value. Watch what happens as t changes. The point r slides smoothly along the line. Written component by component, r equals 1 plus t, 2t, and 5 minus t. Next, the dot product. For 2 vectors u and v, the dot product equals u sub x times v sub x plus u sub y times v sub y plus u sub z times v sub z. This connects directly to the angle between them. The dot product of u and v also equals the magnitude of u times the magnitude of v times cosine of theta. Let's use u equals 1, 0, 0 and v equals 1, 1, 0. The dot product of u and v equals 1 times 1 plus 0 times 1 plus 0 times 0, which equals 1. Now the magnitude of u is 1 and the magnitude of v is the square root of 1 squared plus 1 squared, which is the square root of 2. So cosine of theta equals 1 divided by 1 times the square root of 2. Taking the inverse cosine of that gives theta equals 45 degrees. Now the cross product. Given 2 vectors, u and v, their cross product produces a brand new vector that is perpendicular to both of the originals. Using u equals 1, 0, 0 and v equals 0, 1, 0, the cross product of u and v works out to 0, 0, 1. This new vector points straight up, perpendicular to both u and v, and it's exactly the kind of normal vector we need to define a plane. A plane is defined by one point sitting on it, plus a normal vector perpendicular to its surface. Let's use the point 1, 0, 2, together with the normal vector 0, 0, 1 that we just found from the cross product. The plane equation comes from saying the normal vector, dotted with the vector from our known point to any point x, y, z on the plane, equals 0. That gives 0 times x minus 1 plus 0 times y minus 0 plus 1 times z minus 2 equals 0. Expanding that out, the 0 terms vanish, leaving simply z minus 2 equals 0. So in a x plus by plus cz equals d form, this plane is 0x plus 0, y plus 1z equals 2, or just z equals 2. Finally, let's find where our line meets this plane. We substitute the line's coordinates directly into the plane equation. Our line gave z equals 5 minus t, and the plane says z equals 2. Setting these equal, 5 minus t equals 2. Solving for t, subtract 5 from both sides to get minus t equals minus 3. Watch the sign carefully here, both sides flip together, so dividing by minus 1 gives t equals positive 3, not negative 3. Substituting t equals 3 back into the line, r equals 1 plus 3, 2 times we're viewing it flat in 2 dimensions. Step 1. Write each vector in component form. Step 2. Find its magnitude using the square root of the sum of squares. Step 3. Build a line as a point plus t times a direction vector. Step 4. Use the dot product to find the angle between 2 vectors. Step 5. Use the cross product to find a vector normal to a plane. Step 6. Build the plane equation from a point and its normal. Step 7. Substitute the line into the plane equation and solve for t to find the intersection point. The single most common mistake here is a sign error when solving for t. Always check both sides of the equation, Keep matching signs before you divide. In short, vectors have length and direction. A line is a point plus a direction vector times a parameter. A plane is a point plus a normal vector. And an intersection comes from substituting one equation into the other and solving for the unknown.